Alright guys, good morning. So I want to start today's lesson with a little bit of a homework review. If there's any questions from the homework that you guys would want me to go over, I can go over them now. So I'm talking about homework number 1, which was the one that I assigned last Thursday. So you guys can go ahead and type in the number that you want to see me work out if there's any questions. If not, then we can just get started on the lesson. Okay, alright. Then we'll just go ahead and get started with the notes then, if there's no questions. If there are, then maybe we can look at them at the end, for those of you who do join a little bit later. Okay, so let's go ahead and start here with a little bit of vocab. So last time we took a look at the imaginary number I. So today we're going to look at the complex number. And we discussed a little bit about this last time. Remember, I made a little diagram here that the complex numbers is where the imaginary numbers are included, right? So imaginary simply is a subset of the complex numbers. So today we're going to take a look at the complex numbers in more detail. All right, so the imaginary number has a formal definition that we didn't talk about last time, so I'm going to introduce it today. So an imaginary number it's a number in the form a plus bi, okay, where a and b are real numbers, okay, typically, however, to get an imaginary number, the a has to be 0. Okay, a has to be 0, because then what that allows the imaginary number to be is just the second half, right? So a can be 0, a must be 0, but b cannot be 0. Okay, the reason for that is, for example, let's say you have an imaginary number, a plus bi, right? Now imagine that a is 0, right? So you have 0 plus, and then b can be anything else. It could be any other number except 0. Well, then let's say it was 3. Okay, well, notice what you end up with here was, instead of having 0 plus 3i, that's just 3i, right? So you see how this right here, that's the imaginary number. Okay, so there's a difference between an imaginary number and a complex number, and so that's what the next definition that we see comes in. So now instead, right, take a look at the definition for a complex number. Where a is equal to 0 and b is not equal to 0. A complex number is a number of the form again, it's still a plus bi, where a and b are real numbers. Okay. A is considered the real part. B, the imaginary part. Right, so here A and B don't have restrictions on what numbers they can be, obviously, as long as B is not equal to 0. Okay, so a complex number still has that restriction where B is not equal to 0, because if B becomes 0 and 0 times I is 0, then you lose the imaginary part that makes it a complex number. Okay, so if you think about what this is saying, then you have a complex number. A complex number is made up of two parts. You have your A and you have your B. So just imagine, right, if A, let's say A was 4 and B was 2, you could end up with a complex number that looks like 4 plus 2i. Okay, in this case, 4 represents the real component of the number, whereas the 2i represents the imaginary part. So a complex number is made up of a real number plus an imaginary number. However, those numbers don't mix, right? This does not end up being 6i, okay? It's for the same reasons as why 4 plus 2x would not be 6x, right? Because they're not like terms, okay? So just so you can see that they're supposed to stay separate. They're supposed to be in that form, a plus bi. A real number, a whole number, or it could be a decimal, but it's a number that does not have the I, plus a number that does have I. Okay, so do you see how an imaginary number simply just represents the second part, the second half, right? So if it's a number that doesn't have anything added to it in the front, like 3i, right, that's what we can call imaginary. Once the number has two parts to it, now it's read as a complex number. Okay, so that's the subtle difference. Imaginary is when it's just a number with I. The complex is when you have two numbers, one plus the imaginary, a real one plus the imaginary, then it becomes complex. Okay, all right. Okay, so today what we're going to look at is a little bit of the just the adding and subtracting some complex numbers. Okay, so it's going to involve a little bit of what we talked about last time, which was converting numbers with square roots that are negative, converting them into I, and then once we have them converted to I, then we can have a lot more flexibility with them in terms of, you know, adding and subtracting them. Okay. All right, so let's go ahead and move on to that. All right, so just a kind of quick definition of what a sum of a complex number looks like. So sum of complex number. Okay, and here's a basic one. So let's say you had a plus bi, right? That is a complex number, plus another complex number, we'll call it c plus di. Okay, here what you're going to do is you're basically going to add the way you would if they were like terms. Okay, so I want you to identify which ones are allowed to be added together. I can add the a plus the c, and I can also add the b, oops, I can also add the b with the d. Why? Because those are the like terms. Okay, so then eventually what you get is this complex number that's going to say a plus c, right? Notice how both of these here represents the real. plus b plus d, and because these both share I, right, when you combine them, it's just going to have I. It's not like multiplying. You're combining like terms. So b plus di, it's just b plus d with the I out front. And then this represents the imaginary portion. Okay, so you still have your real plus your imaginary. Okay, so as we go through this, remember that you're going to need to write a sum. You're going to need to have the real number in the front with the plus or minus the imaginary number in the back. Okay. All right, so let's take a look at the first example then. And we have 3 times the square root of negative 2 minus the square root of negative 50. Okay, so remember the first thing that we talked about last time was you always want to extract the I first. Okay, here you're subtracting, right? Same thing as the sum, adding and subtracting, same idea. Okay, so the first thing you want to do is convert these two back into I. All right, so I know that I can take 3 square root of 2, but because I've now made that square root of negative 2 into positive 2, the I comes out. Okay, so now what I'm dealing with here is this is an imaginary number, right? 3 square root of 2, that number right there is part of the imaginary. Okay, minus, same thing here, square root of negative 50, well, that becomes 50 with the I out front. Okay, now you see how square root of 50 is not simplified all the way down, so we need to go ahead and do that. So I can go ahead and take 50, build a factor tree from that, and probably 2 terms that multiply to be 50, we could do 5 and 10. Okay, now 50 is no longer active because we factored it down, so then now we try to factor 10, which is 2 times 5. Okay, 10 is no longer active. Remember what we're looking for. In this case, we're looking for a pair of numbers, so the pair represented by the 5 times the 5. Okay, but what was alone? The 2. Okay, so then we can rewrite the square root of 50 as 5 times the square root of 2. Remember that the pair escapes, and if you get boxed, you go back inside. Okay, so really what we end up with now is 3 square root of 2i minus 5 square root of 2i. Okay, so now I want you to think about what could be done here. Remember that you want to treat these numbers in the front as coefficients. Right? Imagine that this represents that you have 3 square roots of 2i minus 5 square roots of 2i. Okay? What you're allowed to do here is you can simplify. Right? These are coefficients. So think of them as if it was 3x minus 5x. Right? You're allowed to do that because these are the exact same thing. Square root of 2i, square root of 2i. Okay, so then what becomes the solution? You get 3 minus 5, so that's negative 2, and then it's like combining like terms, so then it's a square root of 2i that comes down. Okay, so that's the answer right there. Are there any questions on how I got this? Notice that this would be this if we were to try to write it in a complex number. The answer that we got was simply imaginary. We didn't get any real components to this problem. Okay, there was nothing real that we could combine together. So if you were to think of it as how would this look if we had to put the real and the imaginary, it would basically be 0 minus 2 root 2i. Okay, and the 0 would represent the real, versus the negative 2 root 2i represents the imaginary. Okay. All right. So let's go ahead and try a different example. Let's try example 2. Okay. Example 2. We have square root of square root of negative 3 plus square root of negative 27. how does the 2 inside the square root stay the same? Okay, because I want you to think of this as it being okay, when you're subtracting, you're not allowed to subtract the insides of square roots, right? It's like thinking of the square root of 5 minus the square root of 7. Would you say that that is equal to the square root of -2? No, right? So the idea here is that the square root of 2, imagine that you have 3 groups of square root of 2, and then you have 5 groups of square root of 2, right? And then you subtract those, right? How many are you left with? That's the idea, okay? So the insides of square roots cannot be subtracted from each other anyway, okay? The only time we were allowed to do that in the previous example was when there was a product. So let me go back, right? This is what we're allowed to do. If there is a product of numbers, right? If it's a product of square roots, then you can multiply those two numbers together. But it doesn't work with subtraction, okay? So it has to stay as a square root of 2. Okay, so I hope that helps answer your question. Okay, so again, the idea is the coefficient, the number outside of the square root, those numbers you can combine if they both have square root of 2i behind it. Okay, so you want to think of this as this is the like term. Okay. All right, so let's clean up here. Remember, we'll convert to extract the I if possible, right? So we can get the square root of 3i out front, plus this would be square root of 27 with the I. Okay, so now square root of 27 not cleaned up all the way, so here we go and approach it with a factor tree, right? 27 could be 9 times 3. 27 no longer active. Now we factor 9 into 3 times 3. Okay, 9 is no longer active. Okay, so you have 3 3s there. All right, you need a pair. You need a group of 2. So you have a group of 2 right here, and then you have this one by itself. All right, so now you know that the square root of 27, the 3 goes outside, and the one that's in the box goes inside. Okay, so this then becomes 3 square root of 3i. Okay, and then you can bring down the rest, square root of 3i. Okay, now this is very similar to what we did before, right? In the previous example, notice that they both have square root of 3i, right? That is essentially, think of this as it being your variable. If they have the same variable, then you can add what? You can add the coefficients. Well, square root of 3i, this one doesn't have a coefficient, but if there's not anything there, you can draw a 1, right? So then in reality, what do you have as a total, right? You have 1 plus 3. So in total, you could say that you have 4 of what? You have 4 square root of 3i's, okay? That is what you have. So then this becomes your solution here. Okay, again, this one only represents the imaginary part, because if it were to be complex, then you would have needed a 0, because there is no real part to this problem. Okay, it's all imaginary. Okay. Questions there? How we doing? All right. Let me know. Okay. Let's move on to example number 3. Example 3. Okay, so for example 3, we got something a little longer. We got square root of -3c squared plus square root of -27c squared minus square root of 45c squared. All right, so let's clean this up as much as we can. So let's take a look. I have here the square root of 3c squared. Now I want to break this up a little bit. I know that this becomes the square root of -3 times the square root of c squared. Okay, now why do I do that? Well, the intention is I want you to see that I can square root part of it, just not the number, right? I can square root c squared, and then when these cancel, that gives me c, right? If I were to try to clean up the square root of -3, well, that becomes the square root of 3i with the variable c outside as well, okay? Now, it could also work where you could have c move it to the front. So if you didn't want to try to combine and mix these two, just remember it's a product. So I could always move it so it could be c square root of 3i. And I think I like that better because it separates my variable from my imaginary, okay? Now the same thing happens here. I could have the square root of -27 times the square root of c squared, all right? And so in this case, now I can say that this is the square root of 27i times, here c and c squared cancel, so I drop the c. Again, same thing, and we know that the square root of 27, we know what that is because we just did it in the previous problem, right? So I can go ahead and simplify it because I know square root of 27 is the same as 3 square root 3. So I could then rewrite 27 as 3 square root 3i. Okay, now where do you think it might make the most sense to bring the c, right? Should I bring the c here in front? Okay, that looks a little awkward. So then maybe I can write it instead as 3c square root of 3i. Okay, now do you see why I'm building it that way? There's a reason, because I'm leaving square root of 3i at the end, because then whatever's in the front could then become my coefficients, things that I can combine together, all right? And then finally, this last one, minus the square root of 45 times c squared. Okay, well here I don't have a negative inside the square root, so this tells me something. This tells me that this number is most likely going to be real, right? There's no I that's going to come out of this, so I can still break this down. That leaves me with c. I gotta do a little scratch work on the side and take 45 and break it into a factor tree. So 45 could be 9 times 5, and then this becomes 3 times 3, right? So these no longer active. So here I can see what my pair is, right? My pair is 3, and then unfortunately this guy goes back to jail, right? That's a 5. So then in reality, this square root of 45 is the same as 3 square root of 5. Okay, so I would have 3 square root of 5 with the c, okay? And obviously that's a subtraction. Now I want to be consistent. Notice where I've been putting the c in all of the other ones, right? I've been putting the c here in the front, and obviously if there is a number, then I put the number first. So for this example, I'm going to go ahead and do the same. I have minus 3c square root of 5. Okay. And now here's where we got to think a little bit about how the imaginary number looks. Remember that the imaginary number, the complex number is a plus bi. So that means I want my real number in the front. Well, which one of these is my real number? The entire real expression is this part. Okay? Because none of this contains an I. So then that's what needs to be written first. Negative 3c square root of 5. Okay, then I can bring down the other two, and then at some point I'm going to have to combine them. So then I can bring down the c square root of 3i plus 3c square root of 3i. Okay, now since both of these are imaginary, right, notice the like term right here, right? Because they both have square root of 3i, what am I allowed to add? I'm allowed to add the coefficients. Now they see how they both have c in front of them. That means this guy has a 3c. If there is no number in front of the c, that means it's a 1, right? So again, it's very much like, do they have the same pieces that you are allowed to bring them together? Because this one has a 1c plus a 3c, those can combine, right? They both have to have c as well, right? If it was one, if this one was just 1 and this was just 3c, I would have to leave them separate, right? Because they don't have everything that they need in order to be combined, right? It's almost like trying to add x plus xy, right? You can't do it. You can't say that this is 2xy. That's not true, right? They both need x and they both need y in order for you to combine them, right? let's say that this is 3xy and this is 4xy. Because they both have x and they both have y, then I can combine the 3 and the 4 and say this is 7xy. It's the same thing here, right? So because they both have c and they both have square root of 3i, I can combine these coefficients and call this 4c square root of 3 with the I outside. Okay, and then obviously bring down the real number so that it's written as a final expression. So then bring down the plus, bring down negative 3 square root, or 3c square root of 5. Okay, so our final expression here is represented by this solution here. Definitely a start problem. It's a little bit more on the challenging side. Are there any questions on this one? All right, let's move on to example 4. And example 4 is pretty similar, so I think you can apply what we just learned in the previous one. Okay, so example 4, here's what we have. Square root of negative 25a to the third minus square root of negative 225a to the third plus 20a root negative a. Okay, so let's break this up similar to what we did before, right? We can see that this would be the square root of negative 25 times the square root of a to the third. Okay, starting with the square root of 25, well, I can see that that becomes square root of 25i. Right, so then the square root of 25, that's just 5, so I get 5i. And now on this side, I have a to the third, but I'm square rooting that, so I require a little bit of a factor tree, because a to the third is like a times a times a, right? But if I'm square rooting, I'm looking for a pair, so really I can pair that up, but then one of the a's is going to have to go back inside, so this then becomes a square root of a. Okay, so now when I bring it down here and I have a product, remember that the variable on the outside, okay, just like we did with c, I want to pair that with the 5 so that this becomes 5a square root of a, and then the I is what ends up being the final term. Okay. Next one, we got minus. Now we got the square root of negative 225 times the square root of a to the third. Okay, I'm splitting them up because I want to deal with the number and then the variable separately. So again, here I have minus square root of 225i, right? By converting and making that negative from the inside of the square root positive, I have to pull the I outside. And then lucky for us, the square root of 225 is actually a nice number. Let's look for it here. Never mind, don't need that. Okay, you're gonna get 15. So that would be 15i. Okay, and then again, you have the square root of a to the third. Well, you already know what that becomes. It becomes a times square root of a. So when you bring this down and you try to write it all as one term, you want the coefficient, the number first, then the variable that's on the outside. So you got negative 15a, then the square root term, which is a, and then finally the I comes down. Okay, and then finally, okay, let's go down to the last term. The last term, you have 20a, and then this one, you could break this up. Now you could say, well, because I don't want the negative inside, now I can bring down the a, and then also the I comes on the outside. Okay, so now lucky for us, this is already kind of in the same form that all of the other ones are, right? Look, the numbers in the front, followed by the variable a, followed by the square root of a, and then followed by I at the end, right? So I'm going to just go ahead and bring this down. Right, there's nothing more we can do to clean that up. So now notice, again, you want to see if you can combine all of these coefficients together, right? Do they all have the same things? Well, do they all have I? Yes. I'm sorry, do they all have a? Yes. Do they all have the square root of a? Yes. And do they all have I, right? Because if they all have I, then they all fit under the imaginary category, which they do, right? Which then allows you to then combine the 5 with the negative 15 with the positive 20, right? So you combine these three coefficients now, right? 5 minus 15 would give you negative 10, and then negative 10 plus 20 puts you back at 10. Okay, so you end up with 10a square root of a I. Right, because it's combining like terms. You want to think of the a square root of a times I. You want to think of this entire piece as being one variable, right? So then that's what allows you to combine the 5 with the negative 15 and the 20. Okay, and that's pretty much it. Okay, so that's what we get for this expression. All right, so it helps to break it up into pieces, starting from the beginning, right? Breaking it up into these two pieces and dealing with the number first and then dealing with the variable second. I think it helps, but if you can make the jump from the first step down to about this step right here, then feel free. Okay, two more examples and then we'll be done. Okay, so let's take a look at, so actually example 3 and example 4 were actually the hardest two examples that you're going to see for today. The rest are actually a lot easier than this. The reason why 3 and 4 are difficult is because you start within a term that's a square inside of a square root, so they don't look like complex numbers and they don't look like imaginary numbers. You have to make the conversions first, and so then it requires a lot more work. Example 5 and example 6 is just pretty much following the rules of distributive property and then combining like terms. Okay, so if we look at example 5, here's what you get. You get 4 minus 2i, right? So look, this number is already a complex number, right? It's kind of nice. You're going to add that to another complex number, which is 3 minus 3i. Okay, also pretty nice. Plus negative 4 plus 7i. Okay, so now here's what I want to do. Notice how there's addition signs in between each one of them. That means that if I were to distribute that positive, it doesn't change the number that comes behind it. So I could go ahead and just drop the parentheses and combine everything, right? Try to combine everything that is a like term. Okay, so what I see here is, okay, I have a couple that I can combine because they're real numbers, right? So I have 4, I have positive 3, and then here I have this negative 4. Okay, so if I were to combine those three together, 4 plus 3 is 7, minus 4, I get back down to 3. Okay, so that's combining my real numbers together. Now then I can look for everything that's not a real number. I can look for the imaginary numbers and I can combine those together. Right, so negative 2i, negative 3i, and then positive 7i. These are all imaginary, so I can combine these three together. So negative 2 minus 3i is negative 5i plus 7i. Well, that takes us back up to a positive 2i. Okay, so then here is my final solution. 3 plus 2i, right? So now I've written this number as a complex number where I have both the real component as a 3, and then I have the 2i as the imaginary component. Okay, so it's a lot more simple, right? When you don't have to make the conversion from the square root to the imaginary number. Okay, are we good on that so far? Right. Oh, okay. And now, last one. For example 6. So 3 minus 2i, and now we're going to subtract the complex number from it. 2 minus 3i. Okay, so here you just have to be aware that if you have a minus sign in between, then you distribute it first. Okay, so I would distribute first before I clean everything up. Okay, so this negative distributes into the second parenthesis. So then we can rewrite this as 3 minus 2i minus 2 plus 3i. Okay. So again, combine your real values. You have a 3, you have a negative 2. Combine your imaginary values. You have a negative 2i with a positive 3i. Okay, so here's what we can say. I have 3 minus 2. That's just 1. And then I also have negative 2i plus 3i. Well, that's going to be a positive 1i. Okay, so you could leave it as 1 plus 1i, or you could write it as 1 plus I. And then that becomes your final expression. Okay, so that's pretty much it for today. Those are the examples that I wanted to go over. I will upload the homework, so you'll see it in a few minutes. So let me give you an idea of what that's going to look like. Okay, so that'll be the homework. So you get to see a little bit of everything that we did in the notes. So pretty straightforward. And then the solutions are down here at the bottom, so you can check your work to make sure that you're on the right track. Okay. So I know some of these solutions look a little funny, like 17 and 18, right? Notice that they put the I in the front of the square root. That's technically not how it should be written. The I should always be at the end. Okay, so just something to keep track of and be aware of. Okay, but other than that, do you guys have any questions for me regarding the notes? Okay, I'll also post an announcement regarding retaking Unit 5 test. So I know some of you were asking about it, and I've gotten emails from other kids in other classes as well who are a little bit worried about it. So I will find a way to get that information out to you. Most likely what I will do is that I will create a video showing you how to correctly do each one of the problems so that you can study from that. I can also send you your test. So I'll send you like a PDF version of your test, the one that you took, and then you can identify which problems are the ones that you didn't get correct. So then, just like before, you do corrections. You send me proof of your corrections. Again, anything that you didn't get a 4 on, you do a correction on it. Obviously, you'll have the video of me guiding you how to do it correctly, and then I'll upload a retake soon. I don't have it written yet, and I'll have to collaborate with the other Algebra 2 teachers to get it done. But there will be possibility for a retake. Okay, so it's coming. Just stay patient. I know that some of you guys are worried about your grades. Okay, so just stay posted. Okay, so I'll try to like get the information out quickly. Okay, at least by tomorrow, by the end of the day tomorrow. Okay. All right, guys. Well, then that's it for today. Obviously, take care of the homework. I think I'm also gonna assign an IXL, so I'll put that on the announcement as well, just to make sure that if people aren't doing the homework, then at least they're staying on top of IXL. Worst case scenario. Okay. So have a good day, have a good afternoon, and I'll catch you guys on Thursday. Okay. Take care.